Hello, everyone, and welcome. My name is Matsani bin Katan. So, in engineering mechanics, everything we look at, from the smallest gear to the biggest bridge, involves physical quantities. But the way we describe them, well, that's absolutely crucial. It's not always enough to just throw a number at it. Today, we're going to dive deep into the really essential difference between two types of quantities, scalars and vectors.
Take a look at this bridge. It's held up by these huge cables, and each one is under some incredible tension. Now, to analyze a structure like this and make sure it's safe, we have to ask ourselves a really critical question. Is it enough just to know how much force is in each cable, or is the direction of that pull just as important? The answer to that question is really the key to everything we're going to discuss.
You see, in the world of engineering mechanics, not all numbers are created equal. Some quantities are simple, right? You say a number and that's it. You've given all the information you need. But for other quantities, a number all by itself is, well, dangerously incomplete.
So, let's start with the simple ones. We call these scalars. The easiest way to think about them is that they answer one basic question: how much? It's all about the size, or what we call the magnitude, of something.
Now, the keyword in this definition is completely. A scalar quantity is fully 100% described by a single value, its magnitude. That's all you need. If I tell you the mass of an object is 10 kilograms, there's literally nothing else to say about its mass. The description is complete.
And the thing is, we use scalars all the time, probably without even realizing it. Mass, like we just said. Time, 30 seconds. Length, 2 meters. The total distance you ran this morning. The temperature outside. All of these are scalars because a single number tells you everything. You don't say it's 30 degrees Celsius to the left. It just doesn't make sense.
Okay, let's pause for a quick check here. Think about your own body mass. When you step on a scale and it says, 70 kilograms, have you described your mass completely? Or is there some kind of direction involved? Of course not, right? Mass is a perfect textbook example of a scalar quantity.
Okay, so now we get to the other half of the story. If scalars are all about how much, then vectors have to answer two questions: how much and which way. And this is how we solve the problem of that bridge from the beginning.
So here's the formal definition. A vector needs two pieces of information to be complete: its magnitude, just like a scalar, but also its direction. If you leave out the direction, the information is pretty much useless for a vector quantity. And for us, in this course, in statics, the single most important vector we're going to deal with is force. I mean, think about it. A force is always a push or a pull. It's just impossible to imagine a push or a pull that doesn't have both a certain amount of strength, that's the magnitude, and a specific direction. This diagram shows us exactly how we represent a vector. We use an arrow. The length of that arrow, that represents the magnitude. So a longer arrow means a stronger force, maybe 100 newtons. The arrowhead itself shows the direction, or its line of action. And we define that direction very precisely with an angle, in this case, 30 degrees from the horizontal. And finally, you've got the point of application, which shows exactly where the force is acting on the body. It really is a complete set of instructions.
So, here's another question for you. Let's imagine you have two forces, and both of them are exactly 100 newtons. Can these two forces actually be different from each other? Think back to what makes a vector a vector.
The answer is absolutely yes. A 100 Newton force pushing an object to the right is going to have a completely different effect than a 100 Newton force pulling that same object straight up. Same magnitude, but different direction. And because of that, they are different vectors with very, very different outcomes. Okay, so to make sure this is all crystal clear, let's put these two concepts side by side and just compare them directly. Getting this distinction right is absolutely fundamental. This table really sums it up perfectly. On the left, you've got your scalars, defined by magnitude only. Examples like time and mass. And on the right, you have vectors, which need both magnitude and direction. Our star player here is force, but this also includes really important concepts like displacement, velocity, and acceleration. This slide right here highlights a classic and really important comparison. Let's say you run 5 kilometers around a track, and you end up exactly where you started. The distance you traveled is 5 kilometers. That's a scalar. But your displacement, which is a vector, is 0, because your final position is the same as your starting position. Same idea with your car's speedometer. It shows your speed, which is a scalar. But your velocity, that's a vector, 100 kilometers per hour heading north. See the difference? Okay, so we've got the theory down. But why is this so incredibly important?
Well, because in engineering, getting this wrong isn't just a mistake on a test. It's how bridges collapse and how structures fail. So let's look at some real-world examples where ignoring vectors would lead to a total disaster. In a simple system like this one, you've got three forces acting on a single ring. Now, to figure out if this system is in equilibrium, which just means is it stable, we absolutely have to know the magnitude of each pole and the precise angle that each cable is pulling at. If you change just one of those angles, the entire balance of the system changes. Let's step it up to a more complex structure. For this beam to be stable, we have to analyze all the forces. The weight of that bag is pulling straight down. The cables from the pulley are pulling at very specific angles. Every single one of these is a vector, and their combined effect, including all of their directions, is what determines whether that beam holds up or fails. And hey, this isn't just for static structures that stand still. For anything that moves, like this car, vectors are essential. You've got the force of gravity pulling it down, the normal force from the road pushing up, friction fighting its motion, and the force that's actually causing it to accelerate. Every single one of those has a magnitude and a direction that we have to account for if we want to predict the car's motion.
All right, let's wrap this up. We'll nail down the key points one last time before we look ahead at what's coming up next. So here's the big takeaway. If you remember nothing else from our little explainer today, remember this distinction. Scalars tell you about magnitude, that's the how much, but vectors, they add that second critical piece of information, direction, the which way.
And I really can't overstate this enough. You simply cannot begin to correctly analyze any engineering system, I don't care if it's a bridge, an engine, or an airplane, without first mastering the difference between these two types of quantities. It is the absolute foundation of everything we do.
And that leads us to a pretty logical next question, doesn't it? We know that both scalars and vectors have magnitude, but how do we actually measure and express that magnitude? What are the standard systems we use in engineering? Well, that is precisely what we are going to cover in our next topic, the system of units. Thank you.